Hi, my name is Anthony McCluskey, and I'm a cybersecurity specialist. My career in cybersecurity began over 20 years ago in the United States Navy and has continued on in places like Twitter and Comcast and Salesforce. And I'm currently pursuing my Master's of Science in Cybersecurity at LaSalle University in Philadelphia, Pennsylvania. And I've been working in the AI space since at least late 2021, early 2022. And so, with that little bit of context in mind, I want to talk a little bit about the coming security nightmare that is represented by AI agents, AI in general, but especially agentic AI. And so, I want to start with a quick disclosure. This talk is a little bit technical. It's not math heavy, but it is architectural. And if you're not a technical person, you can still follow it, but you may have some questions, which I'm happy to address via email or in the comments. The discussion that I'm going to have is really targeted at people who actually build systems, deploy tools, or are responsible when things go wrong. But almost anybody should be able to follow along. So, over the last few weeks and months, everyone has suddenly decided that AI agents are the future. Microsoft declared 2026 to be the year of the agent. Developers at Google are tweeting praise for agentic coding tools. Claude, Copilot, Devin, and browser agents, IDE agents, and other agents are everywhere. And almost no one is talking seriously about what this does to security. So today, I want to explain why AI agents represent a fundamental security regression, not just a new category of bugs. This is not about one bad implementation. This is about the entire architecture. So let's talk a little bit about what some people call the original sin of computing. To understand why agents are dangerous, we have to go back to the foundation of modern computing. Almost every computer you use today is based on something called the von Neumann architecture. And the key idea is simple. Instructions and data live in the same memory, in the same format. And that design is incredibly powerful. It essentially made modern computing possible. But it also introduced what security people often call the original sin of computer security. The CPU cannot inherently tell the difference between code it is supposed to execute and data that just happens to look like code. And that single flaw is the reason that we have had buffer overflows, remote code execution, stack smashing, memory corruption bugs, and other problems for over 60 years. And for 60 years, we've had mitigations, not fixes. The important thing to understand is that we've never fixed this problem. We've mitigated it. We build safer languages like Go and Rust with type safety and bounds checking and ownership models and safer concurrency. And we add platform protections like data execution prevention, address layer space randomization, stack canaries, and sandboxing. And despite all of that, we still see remote code execution vulnerabilities exploited in the wild every single year. And that's after a half a century of some of the smartest people in the industry working on this problem. So keep that in mind. AI architecture makes this worse. Instead of saying that this is a fragile foundation, let's be careful, AI companies did the exact opposite. Large language models do not just blur the line between code and data, they erase it entirely. When an LLM runs, your prompt, the system instructions, prior outputs, retrieved web pages, emails, documents, and tool outputs all get flattened into one continuous context. At the core of the model, there is no concept of this was an instruction, this was untrusted data, this came from a website, this came from the user. It's all just tokens. From a security perspective, that's a catastrophe. We took the original sin of computing and we deliberately amplified it. So let's talk a little bit about how prompt injection actually works. Let's make it concrete. If you ask an AI to summarize this web page, the AI does not treat the web page that it fetches as inert data. The text of that page becomes a part of the same context as your instructions. If that page contains language that looks like an instruction, the model has no reliable way to know that it should not follow it. And that is prompt injection. If the malicious instruction was not typed by the user, but pulled in indirectly through a web page, an email, a document, or a code base, that's called indirect prompt injection. And this is where agents become especially dangerous. Let's talk about why agents are different and worse. A chatbot that gets confused might say something dumb, but an agent can actually do things. Agents can fetch URLs, they can read email, they can modify files, they can run shell commands, they can commit code, and they can send data over the network. If an agent is tricked, it doesn't just hallucinate, it acts. Anything the agent is allowed to do, a malicious prompt can potentially force it to do. That includes exfiltrating private data, writing malware, encrypting files, installing persistence, connecting to command and control servers, and more. And this isn't theoretical. Security researcher Johann Rehberger has demonstrated this repeatedly. In one example, a web page contains hidden instructions telling an agent to download a file, change the permissions, and execute it, and the agent complies. The result is a reverse shell. The agent becomes a malicious insider, what we call a zombie. There's no exploit, there's no memory corruption, there's no 0 day, it's just language. In another demo, classic social engineering techniques like clickfix were adapted for agents, and the agent is asked to show instructions, and it copies a malicious command into its clipboard and pastes it into its own terminal. The agent literally compromises itself. Developers are even more exposed than most people. If you are a developer using agentic coding tools, things get even worse for you. Rehberger describes what he calls the lethal trifecta: prompt injection, a confused deputy, the AI, and automatic tool execution. Agents that can modify files can be tricked into modifying their own configuration. For example, changing a setting that disables approval prompts. Once that happens, the agent enters what some tools literally call YOLO mode, or you only live once mode. It runs commands without asking. And at this point, your IDE agent is effectively malware with commit access. Even guardrails leak. Agents have been tricked into exfiltrating API keys by rendering image where the secret is embedded in the URL. This is not edge case behavior. This is the architecture doing exactly what it was intended to do. So let's talk about why mitigations will fail. So you'll see lots of blog posts from vendors and people trying to sell you things, claiming that this can be solved with prompt classifiers and reinforcement reminders and markdown sanitation and user confirmation dialogues, but none of this works at scale. Prompt classifiers are trying to detect malicious intent in natural language, and that's far harder than detecting malicious JavaScript. History tells us that attackers will just reroute around it. Telling the AI to be careful is meaningless. If the AI could reliably identify malicious instructions, we wouldn't even be having this conversation. And confirmation dialogues just shift the blame to the users. We already know how well that works. People click through warnings all the time. Attackers train for that. And fundamentally, you cannot solve this with another AI because of a deeper issue. Let's talk about the halting problem and why the halting problem shows up again. The halting problem simply says that you cannot reliably predict whether a given input to one program will cause another program to halt or stop or behave in a dangerous way. And using one AI to scan content for malicious prompts before giving it to another AI does not help, because the first AI is vulnerable to the same class of attack. This is not a tooling problem, this is a theoretical limit. And it's not new, it's a familiar nightmare. If this whole situation feels uncomfortably familiar, it should. We've lived through this kind of architectural mistake before. In the 1990s and the early 2000s, web browsers went through a phase where they were rapidly gaining new capabilities. JavaScript and plugins, embedded media, and rich text advertising networks all expanded what a web page could do. And the attackers noticed immediately. One of the most effective attack techniques of that era was called malvertising. A malicious advertisement would get inserted into an otherwise legitimate ad network. That ad would then be served on perfectly reputable websites, including major news outlets. A user would visit a trusted site, not click anything, and still get compromised. And why did this work? Because browsers were executing code that came from third parties embedded directly into pages that users implicitly trusted. The browser had no meaningful way to say, this is just content versus this is active code that can harm you. Once it was in the page, it ran. We eventually reduced the damage. We added scanning and sandboxing and content security policies and better isolation, but malvertising never truly went away. We just made it harder and less profitable, and that took years. Let's talk about the second parallel, documents that executed you. There's another example that's even closer to what's happening with AI agents. For years, attackers embedded malware into documents, Word files, PDFs, spreadsheets, etc., that the victim would open because the file looked like a normal document, but it contained macros or exploit code that executed automatically. The critical failure was the same. We treated untrusted data as executable instructions. The macros were just automation. Active content in PDFs was just a feature. But those files crossed the boundary into execution, and attackers gained control. We spent decades warning people, do not open attachments from unknown senders, disable macros, treat documents as untrusted. And now look at what agents do. They open documents, they read web pages, they process emails, they summarize code bases, and they do it automatically without a human ever opening the file. From the agent's perspective, all of that untrusted content is just more context, and context can be executable. So why is this worse with agents? At least with malvertising and document malware, there were technical signals that you could look for. JavaScript had syntax and macros had structure, file formats had boundaries, but prompt injection doesn't have any of that. Malicious instructions are written in plain language, and it's the same language that the agent is trained to follow, and it's the same language that we're all typing in our emails and documents anyway. And as agents become more capable, attackers no longer need users to click anything. They just need the agent to look at the wrong thing. That's the lesson that history keeps trying to teach us. When you blur the line between content and execution, attackers will always find a way to cross it. And with Agentic AI, we have blurred that line more completely than we ever have before. So it doesn't all have to be doom and gloom. There are some ways that AI agents could theoretically be run more safely. And so you might want to know, what do you do if you still want to use agents, but you don't want to hand them the keys to your life? The safest answer is that you treat an agent like untrusted code running in a hostile environment, because functionally that's exactly what it is. A more secure approach would look something like this. First, you isolate the agent, You run it in a virtual machine or a container that has no meaningful access to your real system, no shared home directory, no access to your personal documents, no access to SSH keys, no password managers, none of it. And then second, you starve it of credentials. Agents should not have direct access to your GitHub tokens, your Cloud Console sessions, your email, or anything else that you would not hand to a random person on the internet. If the agent needs to work with code, it can work on a local clone. If changes need to be pushed, a human should do that step. Third, make actions explicitly gated. Any command execution, network access, file writes outside of the sandbox, financial transactions, or outbound communications should require deliberate human approval. Not click OK to proceed, but a real pause where you have to review what is about to happen and why. Fourth, you should assume compromise and plan for rollback. If you run agents in a disposable environment, you can reset them to a known clean state. You snapshot the VM, you run the agent, and if anything looks weird, you revert. That single capability, the ability to restore a clean baseline quickly, is one of the most practical ways to limit damage. Now let's be honest, this is inconvenient, and it's slower, and it's more cumbersome. It's the opposite of the frictionless agents will do everything for you future that all the vendors are selling. But that trade-off is kind of the point. If an agent is powerful enough to do meaningful work on your behalf, it's powerful enough to do meaningful harm. So the only responsible posture is to contain it, limit it, and assume that anything it touches could be influenced by an attacker. That's what safer agent use looks like today. Isolation, least privilege, meaningful human approval, and fast recovery. AI agents are not toys. They are not just a faster autocomplete, and they are definitely not drop-in replacements for human employees. They are autonomous systems that act on your behalf inside environments that were never designed to distinguish instructions from untrusted data. Right now, the technology is moving faster than the ability to secure it. The underlying architecture makes entire classes of attacks not just possible, but inevitable. And no amount of blog post mitigations or best practice checklists are going to change that reality. You should be especially wary of sales hype around security promises. For organizations that are eager to deploy agents into production environments, especially into browsers, IDEs, email systems, or internal tools, the most important advice is simple. Slow down. Take a methodical approach. Limit scope. Isolate aggressively. Assume compromise. Design for containment and recovery before you design for convenience or speed. If you cannot clearly explain how an agent could be safely compromised without turning into an incident, then it is not ready for broad deployment. Because once these systems are deeply embedded into workflows, undoing them will be far harder than rolling them out. And if we repeat the mistakes of the early web, we will not be cleaning up a few bugs. We will be living with an entire generation of preventable security failures. The future security nightmare of agents is not hypothetical. The only real question is whether we choose to build it slowly and deliberately or accidentally and at scale.